Cuyahoga Valley National Park. National parks in the USA. When one imagines the national parks of the United States, the mind often drifts toward the monumental geology of the American West. We visualize the geysers of Yellowstone, the granite domes of Yosemite, or the vast arid canyons of Zion. These landscapes are frequently remote, severed from the daily hum of industrial civilization, defined by their isolation and their raw, untouched wilderness. However, the narrative of North American conservation is not solely written in the language of remote wilderness. There exists another category of park, one intimately woven into the fabric of human history and urban proximity, yet possessing a biological and geological complexity that rivals its Western counterparts. This is the story of Cuyahoga Valley National Park. Located in northeast Ohio, positioned between the sprawling metropolitan areas of Cleveland to the north and Akron to the south, this park represents a different kind of natural sanctuary. It is a refuge of green recovering from a century of gray, a testament to the resilience of eastern deciduous forests, and a living laboratory of river ecology. To understand Cuyahoga Valley is to understand the deep time of the Paleozoic era, the sculpting power of the Wisconsin glaciation, and the intricate biological recovery of a watershed that once burned. The identity of Cuyahoga Valley National Park is defined fundamentally by the river that names it. The word Cuyahoga is widely attributed to the Mohawk language, roughly translating to Crooked River. This is a geographically accurate descriptor. The river flows south from its headwaters in Cuyahoga County, dropping down toward Akron, before hitting a geological divide that forces it to execute a sharp U-shaped turn north, flowing eventually into Lake Erie. The park protects 22 miles of this river, encompassing roughly 33,000 acres of river bottomlands, steep valley walls, ravines, and rolling uplands. Unlike the parks established in the 19th century to preserve pristine landscapes, Cuyahoga Valley was designated as a national recreation area in 1974 and elevated to national park status in 2000, specifically to protect a landscape that was under the immediate threat of suburban sprawl. It serves as a vital biological corridor, a ribbon of biodiversity threading through a heavily industrialized region. Its existence preserves a cross-section of the Appalachian Plateau, marking the geological frontier where the rugged high country of the East transitions into the flatter central lowlands of the Midwest. To fully grasp the natural foundations of the park, one must look beneath the soil to the bedrock geology, which tells a story of ancient seas and shifting continents long before the river existed. The rocks exposed in the Cuyahoga Valley date primarily to the Paleozoic era, specifically the Devonian and Mississippian periods, spanning roughly 400 million to 320 million years ago. During the late Devonian period, this region of Ohio was submerged under a relatively deep, stagnant inland sea. The waters were anoxic, meaning they lacked oxygen at the bottom, which prevented the decay of organic matter. As mud and organic debris settled over millions of years, they compressed to form the Ohio Shale and the Cleveland Shale. These shale layers are dark, brittle, and fossil-rich, containing the remains of ancient placoderms, armored fish like the Dunkleosteus, which ruled these prehistoric waters. In the park today, these shale layers form the slippery, erodible foundations of the valley floor and the lower sections of the ravine walls. As geological time progressed into the Mississippian period, the environment changed drastically. The sea grew shallower. To the north, the ancestral mountains of Canada were eroding, and distinct river systems carried sand and sediment down into the Ohio basin. This shift in sedimentation created the Berea sandstone, a coarser, more durable rock that sits atop the softer shales. This stratification is the primary architect of the park's dramatic waterfalls. The mechanism at play here is differential erosion. Because the Berea sandstone is resistant to water erosion, while the underlying Bedford and Cleveland shales are soft and flaky, the water cuts away the soft support from beneath the hard caprock. Eventually, the overhang loses its structural integrity and collapses, causing the waterfall to migrate upstream over millennia. This process is vividly displayed at Brandywine Falls, one of the park's most iconic geologic features, where Brandywine Creek cascades 65 feet over a ledge of Berea sandstone, crashing down into the shale gorge below. Above the Berea sandstone lies the Sharon conglomerate, a rock unit that defines the highest elevations of the park, particularly in the Virginia Kendall unit known as the Ledges. The Sharon conglomerate was deposited during the early Pennsylvanian period by fast-moving, braided streams that carried quartz pebbles from far to the north. If you examine the rock faces at the ledges closely, you can see these smooth, white quartz pebbles embedded in the sandstone matrix. This rock is porous and permeable, acting like a giant sponge. Rainwater soaks into the Sharon conglomerate, filters through it, and then hits the impermeable shale layers beneath. Unable to move down, the water moves laterally, emerging as springs and seeps at the contact line between the rocks. This hydrogeological phenomenon creates a specific microclimate at the ledges that is cooler and moister than the surrounding forest, allowing for the persistence of plant communities that are typically found much further north. While the bedrock provided the canvas, it was the glaciers of the Pleistocene epoch that painted the landscape we see today. The most recent major glacial event, the Wisconsin glaciation, reached its peak roughly 20,000 years ago. A massive ice sheet, thousands of feet thick, ground its way south from Canada, effectively burying the region. As the climate warmed and the glaciers retreated roughly 14,000 years ago, they left behind a chaotic mixture of clay, sand, gravel, and boulders known as glacial till. This till blankets the uplands, creating the rolling topography characteristic of the park. The retreat of the ice also blocked ancient drainage patterns, creating proglacial lakes. The Cuyahoga Valley itself was deepened and widened by the meltwater torrents releasing from these dying glaciers. The steepness of the valley walls and the broad, flat floodplain are direct legacies of these immense hydrological forces. The valley we see today is actually too large to have been carved by the current Cuyahoga River alone. It is a misfit stream, a smaller river occupying a valley carved by a much larger ancestral flow of glacial meltwater. The hydrological dynamics of the modern Cuyahoga River are complex and vital to the park's ecology. The river is a dynamic entity, constantly reshaping its banks through the processes of erosion and deposition. In the floodplain, the river meanders, looping back on itself in sinuous curves. Over time, these loops can become so exaggerated that the river cuts through the narrow neck of the loop during a flood event, leaving behind a crescent-shaped body of water known as an oxbow lake. Within the park, the Stumpy Basin area is a classic example of an old river channel that has been cut off, transforming into a wetland habitat rich in biodiversity. The river's hydrology is also flashy, meaning the water levels rise and fall rapidly in response to rainfall. This is partly due to the steep valley walls and partly due to the urbanization of the surrounding watershed, where impermeable surfaces like parking lots and roads shed water quickly rather than allowing it to soak into the ground. The interaction between the river and the land creates a mosaic of habitats, starting with the riparian zone. This is the interface between the aquatic and terrestrial ecosystems. The banks of the Cuyahoga are lined with sycamore, cottonwood, and silver maple trees. These species are adapted to flood conditions. Their root systems are extensive and fibrous, helping to stabilize the riverbanks against the scouring force of the water. The sycamores, with their distinctive peeling white bark, are particularly iconic in the valley. They are phragophytes, plants that draw water directly from the water table, often signaling the presence of abundant groundwater. This riparian corridor acts as a superhighway for wildlife, providing cover and food for migrating birds and mammals moving through the developed landscape of northeast Ohio. Moving up from the floodplain, the park transitions into vast stretches of deciduous forest. Cuyahoga Valley lies in a tension zone between the beech maple forests common to the north and east, and the oak-hickory forests that dominate drier southern aspects. This overlap creates a high diversity of tree species. In the cool, moist ravines and north-facing slopes, the forest is dominated by sugar maple, American beech, and northern red oak. The understory in these areas is often lush with ferns and wildflowers. Conversely, the drier, south-facing ridges support species more tolerant of drought, such as white oak, black oak, and various hickories. This variation is a result of aspect, the direction a slope faces. South-facing slopes receive more direct solar radiation, increasing evaporation and creating a hotter, drier microclimate, which dictates the species composition of the forest. A unique botanical anomaly within the park is found at the Ritchie Ledges. Here, the geology of the Sharon conglomerate creates a cool, damp environment that supports a relict population of eastern hemlock trees. These evergreen conifers are more typical of Canada or the higher Appalachians. They have persisted here since the last ice age, sheltered by the unique topography of the ledges. The dense canopy of the hemlocks creates deep shade, keeping the soil temperatures low and moisture high. Unfortunately, this stand is currently threatened by the hemlock woolly adelgid, an invasive insect that feeds on the sap of the trees. The potential loss of these hemlocks would represent a significant ecological shift, altering the soil chemistry and the temperature regulation of this unique microhabitat. The forest floor of Cuyahoga Valley is the stage for a spectacular display of spring ephemerals. These are perennial wildflowers that have evolved a specific life strategy to capitalize on the brief window of sunlight in early spring before the canopy trees leaf out. Between March and May, the forest floor is carpeted with species like Virginia bluebells, spring beauties, large-flowered trillium, and trout lilies. These plants must complete their entire above-ground life cycle, sprouting, flowering, and setting seed, in just a few weeks. They rely heavily on temperature cues to emerge. Their existence is fueled by energy stored in underground bulbs and rhizomes during the previous year. This burst of productivity is crucial for early-season pollinators, such as bumblebees and solitary bees, which emerge from hibernation hungry and in need of the nectar and pollen these flowers provide. The fauna of Cuyahoga Valley National Park is as diverse as its flora, representing a remarkable story of recovery. In the mid-20th century, the Cuyahoga River was virtually dead, devoid of fish due to industrial pollution and low oxygen levels. Today, following the Clean Water Act and decades of restoration, the river supports over 60 species of fish. This recovery begins at the bottom of the food web with macroinvertebrates, aquatic insects like mayflies, stoneflies, and caddisflies. These creatures are bioindicators. Their presence signals improved water quality because many of them are highly sensitive to pollution. The return of these insects has allowed fish populations to rebound, including pollution-intolerant species like the smallmouth bass and the northern pike. Steelhead trout, which are anadromous, migrating from the lake up the river to spawn, now run the river and its tributaries, linking the ecology of the park to the broader ecosystem of the Great Lakes. The recovery of the aquatic food web has facilitated the return of apex predators, most notably the North American river otter. Once extirpated from Ohio, otters were reintroduced by the state wildlife agency and have successfully colonized the Cuyahoga River. Otters are a keystone species in the riverine system. They are voracious predators of fish and crayfish, and their presence indicates a healthy, productive fish population. Their energetic swimming and slide-making behaviors are not just play. They mark territory and maintain social bonds. Another semi-aquatic mammal that has reshaped the park is the beaver. Beavers are ecosystem engineers. By damming small tributaries, they create wetlands that slow water velocity, trap sediments, and filter pollutants. The ponds created by beavers kill trees, creating standing dead wood known as snags. These snags are essential for cavity-nesting birds, like wood ducks and woodpeckers. As a beaver pond eventually fills with silt and the beavers move on, the area transitions into a nutrient-rich meadow, demonstrating the process of ecological succession. The avian life of the park is perhaps the most visible indicator of its health. The great blue heron is a signature species of the valley. These large wading birds nest in colonies called rookeries. One of the largest rookeries in the park is located along Bath Road, where dozens of massive stick nests are visible high in the sycamore trees. The herons practice a communal nesting strategy, which provides safety in numbers against predators like raccoons and great horned owls. The physics of their flight is impressive. With a 6-foot wingspan, they are capable of slow, efficient flight, but they require significant energy to take off. This is why they nest high in trees. Gravity assists their initial descent into flight. The park is also a stronghold for the bald eagle. The recovery of the eagle population in the Cuyahoga Valley mirrors the national trend following the ban of DDT. Eagles nest in the tops of large trees near the river, feeding on the now abundant fish. Their return is a biological certification of the river's reduced toxicity levels. Smaller birds, particularly the neotropical migrants, find the park to be a critical stopover. The Cuyahoga Valley acts as a green island in a sea of development, providing fuel and rest for warblers, vireos, and thrushes migrating between South America and the Canadian boreal forest. The diverse habitats, from the riparian lowlands to the oak ridges, support a phenomenon known as resource partitioning. Different warbler species forage at different heights in the trees and on different parts of the branches, reducing competition for insects. For instance, the yellow-throated warbler might forage in the upper canopy of sycamores, while the common yellowthroat stays low in the wetland shrubs. This niche specialization allows a high density of species to coexist in the same geographic area. The terrestrial mammal population is dominated by the white-tailed deer. In the absence of their historic predators, wolves and mountain lions, the deer population in the park has exploded. This creates an ecological challenge known as overbrowsing. Deer prefer to eat native wildflowers and the saplings of oak and maple trees. When their numbers are too high, they can strip the forest understory, creating a, quote, browse line below which little vegetation survives. This alters the future of the forest, as the next generation of canopy trees is eaten before it can mature. It also favors invasive plant species that deer find unpalatable, such as garlic mustard and Japanese barberry. To manage this, the ecosystem relies partially on the coyote. Coyotes in the park have filled the niche of the top terrestrial predator. While they rarely take down adult deer, they prey on fawns and help manage the populations of smaller mammals, like rodents and rabbits. The coyote is a highly adaptable canid, capable of thriving in the interface between the wild park and the surrounding suburbs. Another critical, though often unseen, group of mammals in the park are the bats. Species such as the big brown bat and the little brown bat are essential for insect control, consuming thousands of mosquitoes and moths nightly. They roost in the loose bark of shagbark hickories and in old structures within the park. However, the bat populations face a severe threat from white nose syndrome, a fungal disease that attacks hibernating bats. The fungus grows on their muzzles and wings, causing them to wake up during winter hibernation, burning through their fat reserves and leading to starvation. The limestone caves and mines in the region serve as hibernacula, but the spread of this pathogen has drastically altered the nocturnal food web of the valley. Ecologically, the park is also defined by its wetlands. Beyond the river itself, the valley contains marshes, wet meadows, and rare fen habitats. Fens are distinct from bogs in that they are fed by mineral-rich groundwater rather than just rainwater. This creates a more alkaline chemistry that supports specialized plant life. The wetlands in the Cuyahoga Valley act as the kidneys of the watershed. Plants like cattails, sedges, and rushes have root systems that trap sediments and absorb excess nutrients like nitrogen and phosphorus from agricultural runoff. This biofiltration process significantly improves the quality of water before it enters the main channel of the Cuyahoga River. Furthermore, these wetlands serve as the breeding grounds for amphibians. In early spring, the vernal pools, temporary ponds that dry up in summer, come alive with the mating calls of spring peepers and wood frogs. Because these pools are temporary, they cannot support fish, which makes them safe nurseries for amphibian eggs and larvae. The spotted salamander, a large and elusive amphibian, migrates to these pools on the first warm, rainy nights of spring, a mass movement known as the Big Night. The interactions between these species are governed by the flow of energy through the ecosystem. The sun powers the photosynthesis of the deciduous forest and the algae in the river. This energy is transferred to primary consumers like insects and deer, and then to secondary consumers like insectivorous birds and frogs, and finally to tertiary consumers like the coyote, the eagle, and the otter. Decomposers, fungi, bacteria, and carrion beetles break down the organic matter, returning nutrients to the soil to be taken up again by the plants. This nutrient cycling is particularly rapid in the humid, temperate climate of the valley. A fallen log in the Cuyahoga Valley is quickly colonized by shelf fungi and slime molds, breaking down the cellulose and lignin, turning a dead tree into fertile soil for the next generation of life. Geological instability continues to shape the park. The steep valley walls, composed of layers of sand, silt, and clay, are prone to landslides and slumps. This is a natural geologic hazard. When the clay layers become saturated with water, they act as a lubricant, causing the soil and rock above them to slide downhill. This mass wasting shapes the ravines and constantly refreshes the exposure of bedrock, but it also challenges the maintenance of trails and roads within the park. It is a reminder that the landscape is not static. It is in constant motion, driven by gravity and water. The biological integrity of the park is also maintained by the concept of connectivity. The Cuyahoga River serves as a corridor that connects the genetic pools of species to the south with those near Lake Erie. Without this corridor, populations would become isolated, leading to inbreeding and a loss of genetic diversity. The park creates a continuous strip of habitat that facilitates the movement of seeds, pollen, and animals. For example, the seeds of many riparian plants are hydrocorous, meaning they are dispersed by water. They float downstream to colonize new banks. Birds carry seeds of berries from the uplands to the valley floor. This constant mixing of genetic material is essential for the resilience of the ecosystem in the face of climate change and disease. The changing seasons in the Cuyahoga Valley offer a rhythmic display of these natural processes. In winter, the deciduous forest is dormant, revealing the architectural bones of the landscape, the ridges, the ravines, and the rock ledges. Snow acts as an insulator for the soil and the roots beneath. In spring, the energy stored in roots explodes upward in the form of wildflowers and new leaves. The river swells with snowmelt, scouring its banks. Summer brings the full closure of the canopy, creating a shaded, humid interior forest where ferns thrive. The river flow slows, and the biological activity in the water peaks. Autumn triggers the senescence of the leaves. As chlorophyll breaks down, the anthocyanins and carotenoids are revealed, painting the valley in reds, oranges, and yellows. This is not just a visual spectacle. It is a chemical reclamation process where trees withdraw nutrients from the leaves to store them in their roots for the winter. The fallen leaves then form the leaf litter, which insulates the ground and feeds the decomposers, completing the cycle. Understanding Cuyahoga Valley National Park requires looking beyond the scenery to the systems that create it. It is a place where the ancient history of the Paleozoic seabed meets the recent history of glacial scarring. It is a landscape where the precarious balance of the sandstone on shale creates waterfalls, and where the chemistry of the groundwater dictates the location of fens and hemlock stands. It is a story of biological resilience, where a river once ignited by pollution now supports otters and eagles. The park stands as a functional, breathing ecosystem deeply embedded in the human landscape, demonstrating that nature is not just something found in the remote corners of the continent, but a force that persists, adapts, and thrives even in the midst of urbanization. The valley is a testament to the power of water to carve stone, the power of plants to colonize land, and the intricate web of life that connects the smallest aquatic insect to the soaring raptor. While the geological strata and the recovering river provide the physical stage for the Cuyahoga Valley, the narrative of this landscape is incomplete without understanding the human timeline that runs parallel to the natural one, stretching back thousands of years before the first European maps were drawn. The biological resilience we witness today is not merely a recovery from industrialization. It is the latest chapter in a 12,000-year saga of human interaction with the environment, where the boundaries between culture and nature have always been fluid. The valley has served as a hunting ground, a corridor of trade, a defensive stronghold, and a spiritual landscape, with each era leaving a distinct archaeological signature in the soil. To understand the deep ecology of the park, one must understand how indigenous peoples adapted to the shifting climates and biotic communities of the post-glacial world. The archaeological record of the Cuyahoga Valley begins almost immediately after the retreat of the Wisconsin glaciers. As the ice sheets pulled back to the north, they left behind a tundra-like environment, populated by megafauna such as mastodons and caribou. Into this stark landscape moved the Paleo-Indians, the first humans to inhabit the region, roughly 13,000 to 10,000 years ago. Evidence of their presence is subtle but unmistakable, primarily found in the form of fluted projectile points, such as Clovis points, crafted from high-quality flint. These early inhabitants were highly mobile, nomadic hunters who moved in small bands, following the migration routes of large game through the newly formed valley. They did not build permanent villages or alter the landscape significantly, but their presence marks the beginning of the human relationship with this specific watershed. As the climate warmed and the tundra gave way to spruce fir forests and eventually the deciduous woodlands we recognize today, the human strategies adapted. This era, known as the Archaic period, saw a shift toward a more diversified diet. The river, stabilizing into its current channel, became a focal point for subsistence. archaic peoples exploited the rich aquatic resources, including freshwater mussels, fish, and turtles, while also gathering nuts and seeds from the expanding hardwood forests. The transition to the woodland period, beginning around 3,000 years ago, introduced a profound shift in how humans occupied the Cuyahoga Valley. This era is characterized by the adoption of pottery, the beginnings of horticulture, and the construction of earthworks. The valley was not an isolated backwater. It was connected to the broader Hopewell interaction sphere, a vast trade network that spanned the eastern continent. While the Cuyahoga Valley does not possess the massive geometric earthworks found in southern Ohio, the presence of mounds and specific ceremonial artifacts suggests that the people here participated in this sophisticated cultural and religious exchange. The Everett Village site within the park is a significant archaeological window into this time, revealing how people began to settle in river terraces, utilizing the fertile floodplain soils for early agriculture while continuing to hunt white-tailed deer and elk in the uplands. Perhaps the most distinct cultural footprint in the park belongs to the late prehistoric period, specifically a culture known to archaeologists as the Whittlesey tradition, named after the 19th century geologist Charles Whittlesey. Flourishing from roughly 1000 AD to 1600 AD, the Whittlesey people were maize agriculturalists who established semi-permanent villages on the high, defensible bluffs overlooking the river. This shift to high ground suggests a period of social tension or conflict, necessitating natural fortifications. The steep shale walls of the valley, which create the park's dramatic scenery, served a strategic military purpose for these communities. Sites within the park, such as the South Park site and the Greenwood Village site, have yielded intricate pottery tempered with crushed shell, bone tools, and evidence of a diet heavily reliant on the three sisters, corn, beans, and squash, supplemented by the rich protein sources of the river and forest. The Whittlesey people vanished from the archaeological record just prior to widespread European contact, likely displaced by the Beaver Wars and the ripple effects of colonization occurring further east, leaving the valley temporarily depopulated in the mid-17th century. The strategic importance of the Cuyahoga Valley to native peoples, and later to European powers, hinged on a specific feature of geography, the portage path. This 8-mile trail connected the Cuyahoga River, which flows north to Lake Erie and the Atlantic via the St. Lawrence, to the Tuscarawas River, which flows south into the Muskingum, the Ohio, and eventually the Mississippi. This narrow strip of land was one of the most critical geographic pivots on the North American continent. It allowed a traveler to move by canoe from the Gulf of Mexico to the North Atlantic with only a brief overland carry. For centuries, this path was a neutral ground and a superhighway for the Lenape, Delaware, Ottawa, Ojibwe, Munsee, and Wyandot nations. The park preserves the northern terminus of this portage. It was not merely a trail. It was a conduit for the flow of obsidian from the west, copper from the north, and marine shells from the south. The Old Portage area of the park is thus a landscape of continental significance, where the hydrology of the Mississippi Basin and the Great Lakes Basin nearly touch, separated only by a few miles of glacial till. Understanding the human adaptation to this land requires a deep dive into the climatic forces that shape the biotic communities. The Cuyahoga Valley exists in a region of high climatic variability, heavily influenced by its proximity to Lake Erie. This phenomenon, known as the lake effect, is a primary driver of the local ecology. The park lies just close enough to the lake to be significantly impacted by its thermal mass. In the autumn and early winter, the water of Lake Erie remains relatively warm, retaining the heat of the summer. As cold, dry Arctic air masses sweep down from Canada and move over this warm water, the air warms and picks up moisture, becoming unstable. This warm, moist air rises rapidly, forming clouds and precipitating intense bands of snow as it hits the friction and elevation of the land. The northern reaches of the park often receive significantly more snowfall than the southern areas due to these narrow bands. This deep snowpack is ecologically vital. It insulates the forest floor, protecting the roots of perennials and the burrowing animals from the lethal sub-zero air temperatures. Conversely, in the spring the lake remains cold, chilling the breezes that blow over the valley. This phenomenon, known as the lake lag, retards the development of vegetation. While this might seem detrimental, it is actually a protective mechanism. By delaying the budding of fruit trees and sensitive plants, the cool lake air prevents them from flowering during early warm spells, only to be killed by a late frost. This climatic buffering allows for the survival of plant species that might otherwise be decimated by the region's volatile temperature swings. Furthermore, the valley topography itself creates microclimates. On clear, calm nights, radiational cooling occurs. The ground loses heat to space. Cold air, being denser than warm air, drains off the ridges and settles in the valley floor. This can create a temperature inversion where the river bottom is significantly colder than the surrounding uplands. This frost pocket effect influences the distribution of plant species, often confining sensitive plants to the mid-slope positions where the air is warmer and more stable, a phenomenon known as the thermal belt. The seasonal rhythm of the park dictates the behavior and physiology of its fauna in intricate ways. Winter in the Cuyahoga Valley is not a time of biological stasis, but a shift to a hidden, subterranean world. The interface between the soil and the snowpack is known as the subnivean zone. Heat radiating from the earth melts a small space at the base of the snow, creating a humid, stable microenvironment that stays just around freezing, regardless of how cold the air above becomes. In this dark, narrow tunnel system, small mammals like the short-tailed shrew and the meadow vole remain active all winter. The shrew, with its incredibly high metabolism, must consume its body weight in food daily. It scours the subnivean tunnels for dormant insects, pupae, and even other small mammals. This invisible layer of life sustains the predators that remain active, such as the red fox and the barred owl, who rely on their acute hearing to locate prey moving beneath the snow crust. Physiological adaptations to winter in the park reach their zenith in the amphibians, particularly the wood frog. This species is abundant in the park's wet woodlands. When winter arrives, the wood frog does not dig deep to escape the frost like a toad. Instead, it shelters just under the leaf litter, where it freezes solid. The frog ceases to breathe, its heart stops beating, and up to 65% of the water in its body turns to ice. To survive this, the frog's liver rapidly produces massive amounts of glucose and urea, which are pumped into the cells. These compounds act as cryoprotectants, or biological antifreeze, preventing the formation of sharp ice crystals inside the cells, which would rupture the membranes and kill the animal. The ice forms only in the extracellular spaces. When the spring thaw arrives, the frog thaws from the inside out, the heart restarts spontaneously, and the animal hops away, often being the first amphibian to reach the breeding pools. Spring in the valley is defined by the hydrology of vernal pools. These are temporary, fish-free depressions that fill with snowmelt and spring rains. They are the engine of amphibian biodiversity. The migration to these pools is triggered by a specific set of environmental cues: a night with temperatures above 40 degrees Fahrenheit and steady rain. On such nights, thousands of spotted salamanders emerge from their underground burrows in the forest and march toward the ancestral pools where they were born. This phenomenon involves complex chemical orientation. The the salamanders can likely detect the unique scent signature of their natal pool. Because vernal pools dry up by midsummer, the evolutionary pressure is on rapid development. The eggs must hatch, and the larvae must metamorphose into air-breathing adults before the water vanishes. This race against evaporation drives the entire food web of the pool, from the algal blooms to the fairy shrimp and predatory dragonfly larvae. A unique and scientifically significant biological phenomenon occurs within the salamander populations of the Cuyahoga Valley, involving the Jefferson salamander and a complex of unisexual hybrids. Genetic studies have revealed that many of the salamanders in the park are not simple species, but part of an all-female lineage that steals genetic material from males of other species, a process called kleptogenesis. These unisexual salamanders mate with male Jefferson or blue-spotted salamanders. Sometimes they use the male's sperm only to stimulate egg development without incorporating the DNA. Other times, they incorporate the male chromosome to replace one of their own, or to increase their ploidy, the number of sets of chromosomes becoming triploid or tetraploid. This genomic flexibility is a remarkable evolutionary strategy, allowing these populations to maintain genetic diversity and adaptability without the traditional costs of sexual reproduction. The valley serves as a natural laboratory for studying these complex genomic interactions. Summer brings the peak of invertebrate activity, which sustains the avian breeding season. The relationship between the monarch butterfly and the park's flora is a classic example of coevolution. The monarchs that arrive in the valley are often the great-grandchildren of the generation that wintered in Mexico. They seek out milkweed plants, specifically common milkweed and swamp milkweed, which grow abundantly in the park's old fields and wetlands. The milkweed produces a white, sticky latex containing cardiac glycosides, toxic compounds meant to deter herbivores. The monarch caterpillars have evolved not only to tolerate these toxins, but to sequester them in their bodies, making the caterpillars and the subsequent butterflies toxic to predators like birds. The bright orange and black coloration of the monarch is a distinct aposematic signal, a warning to predators of their foul taste. The decline of milkweed across the Midwest due to herbicide use makes the protected populations within Cuyahoga Valley National Park critical way stations for the preservation of this migration. Beneath the surface of the Cuyahoga River, another hidden life cycle unfolds, that of the freshwater mussels. The park is home to recovering populations of mussels, which are among the most imperiled animals in North America. Their life cycle is inextricably linked to the fish populations. Mussels are filter feeders, siphoning water to consume bacteria and algae, acting as natural water purifiers. However, they cannot move upstream on their own. To disperse, they rely on fish. The female mussel releases microscopic larvae, called glochidia. These larvae are parasitic. They must attach to the gills or fins of a specific host fish species to survive. Some mussels have evolved elaborate lures, fleshy extensions of their mantle that look exactly like a minnow or a worm, to attract a predator fish. When the fish strikes the lure, the mussel blasts it with glochidia. The larvae hitch a ride on the fish, drawing nutrients without killing the host, and eventually drop off weeks later in a new location, metamorphosed into juvenile mussels. This means that to protect the mussel, the park must protect the specific fish species that serves as its host, illustrating the tight interconnectedness of the aquatic ecosystem. The avian residents of the park demonstrate remarkable niche partitioning, allowing similar species to coexist without direct competition. This is clearly visible in the owl populations. The great horned owl is the apex nocturnal predator, large and powerful, hunting in open woodlands and field edges for skunks, rabbits, and even other large birds. They nest very early, often in January, taking over the old nests of red-tailed hawks. Living alongside them is the barred owl, which prefers the dense, mature alluvial forests and swamps. The barred owl hunts distinct prey, often targeting amphibians and crayfish in the wet areas, in addition to small mammals. Their calls differentiate their territories. The deep hooting of the great horned owl contrasts with the "who cooks for you" call of the barred owl. However, the balance is shifting. The barred owl is adaptable and has been expanding its range, occasionally displacing smaller owl species. This dynamic tension is monitored by park biologists to understand the shifting hierarchies of the forest raptors. A newer, darker chapter in the park's biological narrative is the invasion of the emerald ash borer. This metallic green beetle, accidentally introduced from Asia, has devastated the ash tree population in the valley. Ash trees were a dominant component of the floodplain forests and the upland woods. The larvae of the beetle bore under the bark, consuming the phloem and cambium layers, effectively girdling the tree and cutting off the flow of nutrients. The result has been the death of millions of trees, creating, quote, ghost forests of standing deadwood. While this is an ecological tragedy, nature responds with succession. The gaps in the canopy left by the dead ash trees allow sunlight to reach the forest floor, stimulating a surge of growth in the understory. Species like spicebush, elm, and maple are racing to fill the void. The dead snags provide a temporary boom in habitat for woodpeckers, whose populations have spiked in response to the abundance of beetle larvae and nesting sites. This demonstrates the reactive, chaotic nature of ecology. Even a catastrophic loss creates new, albeit different, opportunities for life. The park's fungal life, often overlooked, is the glue that holds the forest together. Beneath the soil of the Cuyahoga Valley lies a vast, microscopic network of mycelium, the vegetative part of fungi. These fungal threads form symbiotic relationships with the roots of trees, known as mycorrhizae. In this mutualistic exchange, the fungi extend the root system of the trees by orders of magnitude, mining the soil for phosphorus, nitrogen, and water, which they deliver to the tree. In return, the tree provides the fungi with sugars produced through photosynthesis. Recent science suggests these networks even connect trees of different species, allowing them to share resources, a wood wide web. In the nutrient-poor soils of the sandstone ledges, this partnership is not just beneficial, but essential for the survival of the forest. The diverse array of mushrooms seen in the autumn, from the bright orange chicken of the woods to the deadly destroying angel, are merely the fruiting bodies of this immense underground infrastructure. The Cuyahoga River itself acts as a thermal refuge during the extremes of the seasons. In the height of summer, when the shallow riffles can become dangerously warm for oxygen-sensitive fish like the steelhead trout, the fish seek out the mouths of cold water tributaries or areas of groundwater upwelling. These distinct thermal zones are critical for the survival of cold water species in a predominantly warm water system. The restoration of the river has focused on removing dams such as the Brecksville Dam and the Canal Diversion Dam. These removals have not only restored the natural flow and sediment transport of the river, but have also reconnected these thermal habitats. Fish can now move freely to find cool water in summer or deep, slow overwintering holes in winter, restoring the functional connectivity that the industrial era had severed. As autumn descends on the valley, a phenomenon known as masting occurs among the nut-bearing trees. Oaks, hickories, and beeches do not produce the same amount of seeds every year. Instead, they synchronize their reproduction in irregular cycles. In a mast year, all the trees of a species will produce a massive overabundance of acorns or nuts, far more than the squirrels, deer, and turkeys can possibly eat. This predator satiation strategy ensures that some seeds will survive to germinate. The following years might see very few nuts produced, starving the predator populations down to manageable levels. This boom and bust cycle ripples through the food web. A heavy mast year leads to better survival for white-footed mice in winter, which in turn can lead to an increase in the tick population, which feed on the mice, and a higher incidence of Lyme disease the following summer. It links the botany of the canopy directly to human health concerns, illustrating the complexity of the biotic interactions. The night sky of the Cuyahoga Valley offers a final perspective on the park's ecological role. While light pollution from Cleveland and Akron is a constant presence, the park preserves a corridor of relative darkness. This is crucial for the nocturnal migration of birds. Most songbirds migrate at night to avoid heat stress and predators, using the stars and the Earth's magnetic field to navigate. Bright city lights can disorient them, causing fatal collisions with buildings or exhaustion. The dark ribbon of the Cuyahoga Valley provides a safe passage, a visual and magnetic guide leading them north to the boreal forest or south to the tropics. The preservation of this dark sky is as much a part of conservation as the protection of the soil or water. In the deepest ravines, where the hemlocks block the sky and the moss covers the sandstone, one can find the northern monkshood, a federally threatened plant species. Its presence here is a relic, a biological echo of a colder past, clinging to existence in the specific microclimate created by the geology and hydrology of the valley. It serves as a reminder of the fragility of these systems. The Cuyahoga Valley is not a static museum of nature. It is a dynamic shifting arena where ancient geological forces, long-term climatic cycles, and the immediate pressures of the modern world collide. From the genetic theft of the salamanders to the engineering of the beavers, and from the deep time of the Paleo-Indian hunters to the recreational hikers of today, the park is a testament to the persistence of life in the spaces between the cities. It is a landscape that demands we look closer, past the scenic vistas, to the molecular, historical, and ecological gears that keep the valley alive. To understand the northern monkshood, or the intricate genetic dance of the salamanders, we must look deeper than the biological present and turn our attention to the immense, slow-moving physical forces that constructed the theater in which these ecological plays are performed. The biological nuance of the Cuyahoga Valley is merely the skin atop a skeleton of rock and ice, a landscape forged by the collision of continents and the grinding weight of glaciers. The specific microclimates that allow for the persistence of rare species are the direct result of a geological architecture that dates back hundreds of millions of years, compounded by a hydrological history that is both ancient and actively evolving. To grasp the full reality of this national park, we must peel back the forest floor and examine the deep time of the Appalachian Basin and the violent climatic shifts of the Pleistocene that sculpted the valley we walk today. The geological narrative of the Cuyahoga Valley begins in the Paleozoic era, specifically during the Devonian period, roughly 400 million years ago. At this time, the land that is now Ohio was located south of the equator and was covered by a warm inland sea. The history of the park's bedrock is essentially a history of this sea's changing depth and oxygen levels. The oldest rocks exposed in the park, visible at the bottom of the deepest ravines and along the river's edge, belong to the Ohio Shale Formation. This rock tells a story of a stagnant anoxic seafloor. The water circulation in this ancient basin was poor, leading to a lack of oxygen at the bottom. As algae, plankton, and early marine organisms died, they sank into the mud. Because there was no oxygen to fuel the bacteria that would normally decompose this organic matter, the carbon was preserved, locked into the sedimentary layers. Over eons of pressure, this organic rich mud lithified into black shale. If you break a piece of fresh Ohio shale, you can sometimes smell a faint odor of petroleum, a chemical memory of that ancient life. This high carbon content makes the shale dark, fissile, and mechanically weak, a factor that drives the erosion patterns we see today. As we move upward in the geological column and forward in time into the Mississippian period, the environment shifted. To the east, the ancestral Appalachian Mountains, the Acadian Mountains, were rising, pushed up by the collision of tectonic plates. As these mountains rose, they immediately began to erode. Massive river systems flowed westward from these high peaks, carrying vast quantities of sand, silt, and clay into the inland sea that covered Ohio. This created a massive delta system, known to geologists as the Catskill Delta. The sediment plumes from this delta slowly filled the basin. The transition from the Ohio Shale to the Bedford Shale represents a shift from the deep, stagnant water to a shallower, more turbid environment, where mud and silt were being deposited by these distant river currents. The Bedford Shale often displays ripple marks, fossilized evidence of the currents that moved across the floor of that ancient sea, preserving the hydrodynamics of a world that existed 360 million years ago. Above the Bedford Shale lies the Berea Sandstone, a rock unit that marks a distinct change in energy. Sandstone is composed of coarser grains than shale, which implies faster-moving water capable of transporting heavier particles. The Berea Sandstone was likely deposited in a deltaic environment, perhaps as barrier islands or sandbars, where waves and currents washed away the finer silts and left behind the durable quartz sand. This rock is the master builder of the park's verticality. It is significantly harder and more resistant to chemical and physical weathering than the shales beneath it. This differential resistance is the engine of the valley's topography. As water flows over the landscape, it easily cuts through the shale, but struggles against the sandstone. This creates the caprock effect, where a ledge of Berea sandstone overhangs a retreating layer of shale, forming the sharp lips of the waterfalls and the steep rims of the gorges. Without this specific stratigraphic sequence, hard rock over soft rock, the Cuyahoga Valley would be a gentle, rolling plain rather than a landscape of ravines and cataracts. The final and uppermost chapter of the bedrock story is the Sharon conglomerate, deposited during the early Pennsylvanian period. By this time, the sea had retreated, and the region was a terrestrial landscape traversed by powerful, braided rivers. The Sharon conglomerate is a sedimentary rock composed of sand and distinctive white quartz pebbles. These pebbles are crucial clues to the past. They are made of vein quartz, a material that formed deep within metamorphic rocks. By tracing the origin of these specific pebbles, geologists have determined that the rivers which deposited the Sharon conglomerate flowed from the north, draining a mountain range in Canada that has since completely eroded away. The energy required to transport these smooth, rounded pebbles hundreds of miles was immense, suggesting a wet climate with torrential river flows. The Sharon conglomerate is highly porous and permeable, acting as a massive aquifer. Rainwater percolates rapidly through this rock until it hits the impermeable shale layers below, forcing the water to move sideways and emerge as springs. This contact line between the Sharon conglomerate and the underlying Meadville Shale creates a specific zone of moisture that dictates the vegetation patterns at the highest elevations of the park, such as the Ritchie Ledges. While the bedrock provided the raw material, the landscape was sculpted by the glaciers of the Pleistocene epoch. This was not a single event, but a cyclical process of freezing and thawing that lasted for 2 million years. The most recent advance, the Wisconsin glaciation, reached its maximum extent about 20,000 years ago. The ice sheet that covered northeast Ohio was not a mere coating of frost. It was a continental glacier, a sheet of ice up to a mile thick, moving under the influence of gravity. The sheer mass of this ice depressed the Earth's crust, pushing it down into the mantle. As the ice moved, it acted as a massive excavator. It did not just slide over the surface. It plucked rocks from the ground, freezing them into its base, and used them as abrasives to grind down the bedrock. This process, known as glacial abrasion, smoothed the sandstone and shale, leaving behind scratches called striations that allow geologists to map the direction of the ice flow. The retreat of the glaciers was as transformative as their advance. As the climate warmed roughly 14,000 years ago, the ice began to melt, but not evenly. The glacier essentially stalled, and the melting edge remained in one general area for a prolonged period. As the ice melted, it dropped the unimaginable load of debris it had been carrying: clay, sand, boulders, and gravel. This unsorted mixture is called glacial till. In the Cuyahoga Valley region, this accumulation formed the Defiance Moraine, a broad, low ridge of debris that runs roughly east-west. This moraine acted as a dam. The meltwater from the retreating glacier was trapped between the ice front to the north and the high ground of the moraine to the south, forming a series of proglacial lakes. Glacial Lake Maumee, the ancestor of Lake Erie, was one such body of water. The drainage from these lakes, seeking an outlet to the ocean, carved new channels. The modern Cuyahoga Valley is, in large part, a sluiceway, a channel deepened and widened by these catastrophic outbursts of glacial meltwater, which possessed a scouring power far greater than the modern river. The peculiar shape of the Cuyahoga River is a direct result of this glacial interference. Prior to the glaciations, the drainage of Ohio was dominated by the Tees River, a massive system that flowed west and north. The glaciers obliterated this ancient river system, burying its valleys in hundreds of feet of till. The Cuyahoga River was born on this chaotic post-glacial surface. It begins its journey flowing south, following the slope of the glacial plateau. However, near Akron, it encounters the Defiance Moraine. Unable to cut through this massive pile of glacial debris to continue south to the Ohio River, the river is forced to turn sharply to the north, finding an older buried valley, a ghost valley from a previous interglacial period, that leads it down to Lake Erie. This U-turn is a geomorphic anomaly that defines the hydrology of the region. It means the river flows down a relatively steep gradient from its headwaters, hits a flat, swampy plateau at the turn, and then tumbles down a steep, rejuvenated valley to the lake, creating a complex profile of energy and sediment transport. The landscape formation processes did not stop when the ice vanished. They continue today through the mechanics of mass wasting. The steep valley walls, composed of layers of permeable sandstone sitting on impermeable shale and clay, create a geological hazard. When heavy rains saturate the ground, the water moves through the upper layers but pools on top of the clay. This lubricates the interface between the rock units. The weight of the waterlogged soil, combined with gravity and the slipperiness of the wet clay, causes sections of the valley wall to detach and slide downward. These rotational slumps and earth flows are characteristic of the Cuyahoga Valley. They result in a hummocky, uneven topography on the valley sides, often characterized by drunken forests, where trees tilt at odd angles as the ground beneath them moves. This instability is a natural process that constantly refreshes the exposure of mineral soil, preventing the forest from becoming a stagnant monoculture and creating openings for pioneer species. The climate that drives these geomorphic and biological processes is fundamentally shaped by the mid-latitude location of the park and its interaction with the Great Lakes. This is a humid continental climate, marked by large seasonal temperature variances. However, the proximity to Lake Erie introduces a distinct thermodynamic modification. Water has a much higher specific heat capacity than land, meaning it takes much more energy to change the temperature of the water than the soil. Consequently, the lake acts as a massive thermal reservoir. In the spring, the water is slow to warm. Air masses moving over the cold lake are chilled, creating a stable, cool layer of marine air that suppresses convection. This results in the, quote, lake lag, which delays the onset of spring phenology in the northern parts of the valley. This delay is ecologically protective. It prevents fruit-bearing trees and delicate wildflowers from blooming during early, deceptive warm spells in March, only to be decimated by a frost in April. The cool lake air keeps them dormant until the danger of hard frost has statistically passed. In the autumn and winter, the thermodynamic relationship flips. The land cools rapidly, but the lake retains the heat of the summer sun. As cold continental polar air masses sweep down from the Canadian Arctic, they pass over the relatively warm waters of Lake Erie. The lower layers of this air mass are heated and humidified by the lake. This warm, moist air becomes buoyant and rises rapidly through the colder air above it, creating instability and cloud formation. As this system moves onshore and hits the friction of the land and the rising elevation of the Appalachian Plateau, which begins in the park, the air is forced upward, cooling and condensing its moisture into snow. This is the mechanism of the lake effect snow. The Cuyahoga Valley sits on the edge of the primary snow belt, but the northern reaches of the park often receive significantly higher snowfall totals than the southern reaches, creating a gradient of winter severity within the park boundaries. This deep, reliable snowpack is an insulator. It creates a subnivean environment where the temperature at the soil surface remains near 32 degrees Fahrenheit, regardless of the air temperature. This allows soil invertebrates, amphibians, and roots to survive winters that would otherwise freeze them lethal solid. The hydrological cycle within the park is intense and flashy. The watershed of the Cuyahoga River is heavily urbanized, with high percentages of impervious surfaces like asphalt and concrete in the surrounding heights. This alters the natural infiltration rates. Instead of soaking into the ground and recharging the aquifer, rainfall runs off immediately into the storm drains and tributaries. This causes the river to rise with frightening speed after a storm, a phenomenon known as flashiness. These rapid fluctuations in water level exert tremendous stress on the riverbanks, accelerating erosion and sediment transport. The river water itself is a suspension of fine clay and silt particles, eroded from the glacial till and the shale bedrock. This high turbidity limits the penetration of sunlight into the water column, which in turn limits the growth of submerged aquatic vegetation. This physical limitation dictates the structure of the aquatic food web, making the system heavily reliant on allochthonous inputs. Organic matter, like leaves and twigs falling into the river from the terrestrial forest, rather than autochthonous production from algae within the river. The ecosystems that emerge from this interplay of geology, ice, and climate are distinct and varied. The upland forests of the Cuyahoga Valley are not uniform. They are a mosaic determined by soil type and aspect. The soils derived from the glacial till are often heavy, clay-rich, and prone to waterlogging. These soils tend to support the beech maple forest community. American beech and sugar maple are shade-tolerant species. Their seedlings can survive for decades in the dim light of the understory. waiting for a gap in the canopy. When an old tree falls, these saplings race upward to fill the void. This gap dynamics is the primary mechanism of forest regeneration. The fall of a massive tree creates a unique microtopography known as pit and mound. The root ball of the falling tree rips up a mass of soil, creating a pit. As the roots decay, the soil slumps into a pile, creating a mound. This creates localized variations in soil moisture and temperature. The pit collects water and organic matter, while the mound remains drier and warmer. This microtopography increases the biodiversity of the forest floor, offering different niches for ferns, mosses, and wildflowers within just a few square meters. In contrast, the soils formed on the ridges and the edges of the valley walls, where the drainage is better and the sun exposure is higher, support the oak-hickory forest. These forests are disturbance-dependent. Oaks are relatively shade-intolerant. They require sunlight to regenerate. Historically, these forests were maintained by periodic fires, either caused by lightning or set intentionally by native peoples to clear underbrush. In the absence of fire in the modern era, there is a slow successional shift occurring, where the shade-tolerant maples are beginning to invade the oak understory, threatening to eventually replace the oaks. This process, known as mesophication, is a major ecological concern, as oaks provide a critical food source, acorns, that maples do not. The loss of oak dominance would ripple through the food web, affecting populations of deer, turkeys, squirrels, and the predators that hunt them. The wetlands of the Cuyahoga Valley are categorized not just by the presence of water, but by the chemistry of that water. The park contains rare habitats known as fens. Unlike bogs, which are fed by rainwater and are acidic, fens are fed by groundwater that has percolated through mineral-rich glacial till or limestone. This groundwater is alkaline and rich in calcium and magnesium. When this water emerges at the surface, the chemistry creates a harsh environment for common plants, but a perfect one for specialists. In these fens, you can find plants that are more typical of the Canadian tundra. The calcium in the water precipitates out to form a marl, a gray, clay-like soil that is essentially unconsolidated limestone. Over thousands of years, this precipitation can form tufa rock, a porous, limestone-like rock that builds up around the mosses and sedges, literally fossilizing the plants while they grow. These fens are geological time capsules, preserving pollen and plant matter that allow scientists to reconstruct the climate history of the region since the last ice age. The floodplain forests represent another distinct ecosystem, governed by the rhythm of inundation. The trees here, sycamore, cottonwood, box elder, and black willow, must tolerate having their roots submerged for weeks at a time. This creates anoxic soil conditions. To survive, these trees have evolved morphological adaptations such as lenticels, enlarged pores on their bark that allow for gas exchange, and adventitious roots that grow from the trunk above the waterline. The physical force of the floods also shapes the forest architecture. Ice flows during the spring thaw scour the bark of the trees on the upstream side, scarring them. The deposition of fresh silt during floods renews the soil fertility, making these bottomlands some of the most productive growing sites in the park. This rapid growth creates a jungle-like density of vegetation, with thick vines of wild grape and Virginia creeper draping the canopy, creating a vertical habitat structure that is preferred by nesting birds like the Baltimore oriole and the warbling vireo. The seasonal changes in the park are not merely visual, but are driven by precise physiological thresholds. The awakening of the forest in spring is a calculated risk taken by plants. The trigger for leaf out is a combination of photoperiod, the length of the day, At accumulated growing degree days, a measure of thermal energy, plants have internal clocks that measure the duration of darkness to determine the season. However, they also track the temperature. If the air warms up too early, the enzymes within the buds activate, converting starches stored in the roots into sugars to fuel rapid cell division. This hydraulic pressure swells the buds until they burst. The spring ephemerals, the wildflowers of the forest floor, operate on an even tighter budget. They must complete their entire photosynthetic cycle before the canopy trees above them fully leaf out and block the sun. This is a race against the shade. By June, the leaves of the trout lily and the spring beauty have withered and vanished, the plants retreating into their underground bulbs to wait in dormancy for another 10 months. Summer in the park is a season of energy capture. The forest canopy acts as a massive solar panel, intercepting over 95% of the sunlight. The interior of the forest becomes a distinct climatic zone, humid, dark, and still. The humidity is generated by the trees themselves through transpiration. A single large oak tree can pump hundreds of gallons of water from the soil into the air in a single day. This evapotranspiration cools the forest, creating a natural air conditioning effect. During this time, the decomposition rate on the forest floor accelerates. Fungi and bacteria thrive in the warm, moist conditions, breaking down the leaf litter from the previous autumn. This nutrient cycling is the heartbeat of the ecosystem, releasing nitrogen and phosphorus back into the soil to be taken up by the thirsty roots of the growing trees. The summer is also the season of the soundscape, dominated by the stridulation of insects. Cicadas, katydids, and crickets use the warm air temperatures to fuel their muscular activity, producing the mating calls that define the auditory environment of the valley. As the tilt of the Earth shifts the northern hemisphere away from the sun, the park enters the senescent phase of autumn. The biological signal for this transition is the lengthening nights. The trees detect this shift and begin a process of withdrawal. They stop producing chlorophyll, the green pigment that facilitates photosynthesis. As the green fades, the other pigments that were present but masked, the yellow xanthophylls and the orange carotenoids, are revealed. Some trees, like the maples and oaks, actively produce new pigments called anthocyanins, which create the brilliant reds and purples. This is not a passive decay, but an active chemical process designed to recover nutrients. The tree pulls nitrogen and phosphorus out of the leaves and stores them in the woody tissues of the branches and roots. Simultaneously, a layer of corky cells, known as the abscission layer, forms at the base of the leaf stem. This layer slowly cuts the connection between the leaf and the branch, sealing the wound to prevent water loss and infection. Eventually, the weight of the leaf or a puff of wind breaks the remaining connection, and the leaf falls. This annual shedding is a massive transfer of biomass from the canopy to the ground, resetting the cycle for the decomposers and insulating the soil for the coming winter. The winter landscape reveals the skeletal structure of the geology. With the leaves gone, the terrace levels of the ancient river are visible, carving benches into the valley walls. The ravines, usually hidden by foliage, display their jagged, youthful profiles, showing where the streams are actively cutting down into the bedrock. The frozen waterfalls hang as suspended sculptures, recording the flow of water and ice. This is the season where the biotic world pauses, and the abiotic world, the rock, the wind, the ice, takes center stage. The freeze-thaw cycles of winter are the primary weathering agent, prying apart the sandstone blocks at the ledges and breaking down the shale into clay. It is a time of geological work where the landscape is prepared for the next cycle of growth. The Cuyahoga Valley, therefore, is a place where the static appearance of the landscape is an illusion. It is a system in constant flux, driven by the tension between the uplift of the land and the erosion of the river. the heat of the summer and the ice of the winter, the growth of the forest and the disturbance of the storm. It is a meeting ground of north and south, where the boreal influence of the glaciers lingers in the cool ravines, and the southern influence of the river basin creeps up the floodplains. To walk through the park is to walk through a cross-section of Earth's history, from the Devonian seas to the Wisconsin ice to the Anthropocene recovery, all layered together in a complex, living stratigraphy.